And there's two possibilities. It's pi over 6 in the first quadrant or pi over 3. But you should see the way I've drawn the picture, which one is it? Because of where it's located, pi over 6, if you've got to think degrees, is 180 divided by 6, which is a 30-degree angle. Pi over 3 is 180 divided by 3 is 60-degree angle. Clearly, that's the 30-degree angle, so I should know right away this is pi over 6. This is related to pi over 6. It's in the second quadrant. It's got to be one of the irreducible multiples. 2 pi over 6 reduces down, 3 pi over 6 reduces down, 4 pi over 6 reduces down. It's got to be 5 pi over 6. So here's 5 pi over 6. Again, look at the unit circle. Pi over 6, second coordinate a half. 5 pi over 6, second coordinate 1/2. So the coordinates of these points is √3 over 2 1/2. And of this one, it's because it's the second quadrant, it's a -1 over √3. So, solving this equation, x is pi over 6, 5 pi over 6, assuming x lies between 0 and 2 pi. Right? We'll get the general solution in a minute. Look at this. Now the second coordinate is a -1/2. So here's the number of -1/2 on the y-axis. That gives you over here, the points on the unit circle where that occurs. A little bit off here. I'm bleeding. So let me be a little bit careful. Halfway down, probably be about there. Okay, so there's one, and the other one right there. So the terminal side here is in the third, terminal side is in the fourth. So there is the number of -1/2. The point here, of course, is in the fourth, so it's going to be √3 over 2 minus 1/2. This was in the third, minus √3 over 2 minus 1/2. And again, I know, without even looking at the unit circle over there, that information written out, this is an irreducible multiple of pi over 6. What's the next one? 6 pi over 6 reduces down, so this is 7 pi over 6. 8 pi over 6 reduces down, so does 9 pi over 6, so does 10 pi over 6. So this one is 11 pi over 6. Where if this equation is asking for all the irreducible multiples of pi over 6. The answer's in the fourth quadrant, so there. So this equation says x is 7 pi over 6, 11 pi over 6, if we assume the standard interval. So that's just to get the process started. Now I can generate the entire solution from each one of these by doing the same thing, adding a multiple of 2 pi. So that's 4 statements to write down. However, if your eyes are open, there's actually a quicker way. Instead of writing down these 4 statements, I can make 2 statements. Why? Because rather than going here and going all the way around 2 pi, I can start here, get a solution, add pi, I get that solution. Add pi, get back to here again. Okay, add pi, get back to here again. So by adding multiples of pi, I pick off these 2 terminal signs. And doing the same thing here, if I have 5 pi over 6 and add pi, I get 11 pi over 6. Add pi, I get back to this point again, and so on and so on and so on. So it's easier to write down the general solution now, just using multiples of pi. I can, and it doesn't matter which point I pick on. If I pick on this and and add multiples of pi, or I pick on this and add a multiples of pi, I'm still picking up the information for these 2 points in the circle. So if I take pi over 6 and add a multiple of pi to it, I'm getting all the solutions here, okay? Or x is equal to, I can pick on 5 pi over 6 and add multiples of pi here. If I want to replace pi over 6 by 7 pi over 6 and add multiples of pi to that, that's fine. If I want to replace 5 pi over 6 by 11 pi over 6 and add multiples of pi to that. Okay? And again, you've got to specify that k is an integer. You must have this. If you don't see that, then, and you write it down this way, I would say pi over 6 plus 2k pi, 5 pi over 6 plus 2k pi, 7 pi over 6 plus 2k pi, 11 pi over 6 plus 2k pi. That's equivalent. That's equal to it. It'll give you the same solution. You just have more work to write down. That's all. But that's correct as well. Okay? Any questions? Okay. The next example, getting a little bit more complicated. Still a single trait expression in the equation, but now there's a complication, there's a wrinkle. The wrinkle, instead of having cosine x, I have cosine 2x. It's a wrinkle. Believe me, it's a wrinkle. Okay, so how do I solve that? Again, this is part C, continuing from the previous page. So I want all solutions. No, I don't. It says restriction. Oh, now this is actually taking this equation, solving for x, but putting a restriction. So now this says go around one complete rotation in the positive direction. So the answer, if there are any solutions to this equation, there's going to be plenty many now. Okay? So what do? I do the same thing I did before. I try and solve for the single trait term. So divide by 2, and very quickly I got root 2, and I got cosine 2x is equal to root 2. And of course, there's the restriction. Only once the values of x, for which cosine twice x is this value, okay, 1 over root 2. As soon as you see 1 over root 2, you should recognize that number as related to pi over 4 in the first quadrant, right? 1 over root 2, 1 over root 2. We want cosine, first coordinate to be 1 over root 2. 1 over root 2, and again, if you don't quite clue into it, if you just look at the number on your calculator, 1 divided by the square root of 2. By the way, that's exactly the same thing as root 2 over 2. They're the same. That's just rationalizing, right? So you'll see it's either form. Is approximately 0.7. First coordinate is approximately 0.7. So that's the x coordinate. 0.7 would be, say, about there. That's approximately 0.7. Allowed to go around once in the positive direction. There actually, I can go up to here, or I can go down to here. There are 2 places where the cosine would be 1 over root 2, or approximately 0.7. There's a point on the circle, and the associated terminal side for the angle